Hello. In this lecture, we're going to talk about sound. And just to get us started, sound is a wave also that moves through the air or any material, actually, but for us, primarily the air. But before we hop too much into that, let's talk about Doppler effect first. And so this is an example of Doppler effect in water. Okay, we're looking at a bug in a pond from above. Just like how we looked at the water from above in that previous lecture. So our bug is sitting here, kind of like treading water or whatever, and sending these waves out. But then what if it starts to move, like move to the right toward B? It's still going to be producing those ripples, but we'll get a pattern like this, where kind of like each place where each wave is generated is moving over. So we kind of have this like compression on the side that the bug is moving toward, and this expansion on the side that the bug is moving away from. And this is because the source of the wave is moving in one direction. And so each subsequent wave has a different center point from like wherever the bug is at that point. And so if we had a different bug on the right side here, it would start to feel those wave crests in close succession. It would like bounce up more frequently. Where if there was a bug on the left side, it would feel those wave crests less frequency, right? This is more frequency. The wave crests are closer together. And this is less frequency. They're farther apart. But yeah, this is the Doppler effect. When the source of the wave is moving, there's a shift in the frequency, um, depending on where you are in relation to the source. So that's what happens when you hear a siren and it makes a different sound as it's coming towards you, passes you, and then when it's going away from you. And that is Doppler effect. It's because it's sending out a sound wave as it travels. And because it's moving, the center of the sound waves, like each subsequent sound wave, is in a different spot. And so when it's moving towards you, you hear it at high frequency because of the Doppler effect. And then when it moves past you, you hear it, and then away from you, you hear it at a low frequency. Okay, but let's talk about like how sound actually works. Well, sort of. First, we're gonna imagine this situation. We have a long room with a closed door on one end and an open window on the other end. If someone opens the door, that would make the air molecules near the door move. Um, as the opening door pushes them, those air molecules. And then these molecules will bump up against those next to them, causing a wave of compression, like the air molecules closer together, to go through the room. And we can look at this illustration to understand it. So initially, they're just like kind of evenly distributed throughout the room. But then we pushed the door open and it compressed some, and then those waves are going to move through like that. Compression is a wave that's going to move through the room to the other side. So that compression, opening the door causes that wave of compression to travel down the room. Then when we close the door, some air molecules are pushed out by the door, like it kind of pulls some out with it. And that leaves a pocket of less dense air. So before we had a pocket of more dense air, now we have one of less dense air. And the rest of the air will spread out to fill that space because it's a gas, and gases spread out to fill any space that they're in. But this void or area of less compression is called rarefaction. So we had compression when we open the door and rarefaction when we close the door. And both of those are sending waves of air molecules, or waves through the air molecules specifically. Another, we're gonna keep looking at this, but first I want to remind you of this part of the previous lecture. We talked about how waves move through a medium. Um, with the slinky as an example. And then we also saw it in this animation of water waves, right? Where it's like the water particles, molecules themselves don't move along the wave. They move a little bit, like the wave makes them move slightly, but the wave itself is moving through the material. The same thing happens with sound, where it's the wave of rarefaction, so spread it, the molecules being more spread out, and the wave of compression that's moving through the air. So that's what we have here. And you can look at these individual particles and see how they just kind of dance back and forth, similar to the water waves. But the wave itself, like if you watch this wave crest, you can watch it move through the particles, right? And then, yeah, the more squished together is that compression, and more spread out is that rarefaction. And that is just sending a wave through particles, like through the air. Yeah, and then we can also see this. So if we have like a tuning fork and some sort of pipe, we can produce a wave in the pipe where we have rarefactions, where the molecules are more spread out, and then compression, where they're more compressed. That part's easy to know. And that's how sound works. Something disturbs the air molecules, sending waves of compression and rarefaction through the air. And eventually that reaches your eardrums, and your eardrums are sensitive to changes in pressure, which is what compression and rarefaction is. Pressure is when things are more compressed or more spread out. So your eardrum notices that. You also, another way to look at this is a speaker, a loudspeaker vibrating. So if you look like closely at a really loud speaker, or just like maybe that's a bad idea for your eardrums, maybe just watch a video of one. You can see it vibrating, like kind of the surface of the speaker, and that is sending sound waves out into the air. And then a microphone, for example, can detect that and show us what it looks like as a regular looking wave instead of this like compression and rarefaction. So it's just showing us like the regular wave pattern that we're familiar with. And we talked about wave speed as depending on the material the wave is traveling through. So if you think about a baseball game and you're watching the batter really closely, like you're just eyes on the batter, you see them swing and hit the ball. And then a little bit later, like maybe a second or so, you hear the crack of the ball hitting the bat. Or another example, you're watching a thunderstorm, you see a bright flash of lightning, and then some time passes, and then you hear the thunder. Those are both examples showing that it takes time for sound to travel to you from the source. So the speed of sound is in air, is 340 meters per second, which is about 760 miles per hour. So it's really fast, but not fast enough that you don't notice a delay, because light travels much faster, as we talked about before. Sound waves also reflect off of different surfaces. So if we think about the wave in the string, how there was like a fixed end and our wave would bounce off of that and reflect back, that's the same kind of thing, but like walls can do that, or really anything for sound waves. So that's what's happening when you hear an echo. If you're like on a cliffside and you shout hello, and then you hear hello, hello. It's a nice replica of an echo. That is because your shout is reflecting off of the other surfaces and then bouncing back to you. And in this picture here, we have a speaker in a room and someone sitting listening, and the sound waves are bouncing off of the different walls and moving in different directions. And this can also distort the sound for the person, right? Because they could get different parts of the wave coming from different directions, and they could end up with interference like we looked at in the last video. There's also refraction, which is when the wave either reaches a different medium or a part of the same medium that's like warmer or colder or something like that, where the sound has different speeds. So for example, in this picture, we have like warm air and cool air, and we have a dog and then someone with a horn. And depending on the refraction, so how much the sound bends and the speed changes, tells us whether or not the dog actually hears the horn and in the way where it like wakes the dog up, for example. And you might a possible experience you could have had if you've been near a lake, you can hear people chatting on the other side of the lake because sound travels through the air and the water. And also at different speeds. And there's also that idea where like if you put your ear to train tracks, you can hear better if a train is coming because it travels faster through the tracks than through the air. Just be careful about that one. Danger options. Okay, let's talk ultrasound. So ultrasound waves are waves with frequencies higher than humans can hear. Like our ears can't pick it up. It's too high of frequency. And when using ultrasounds, we use reflection, so the sound bouncing off a surface, refraction, the sound changing speed depending on material, so like different parts of whatever you're looking at inside the human body or a fetus or what have you. So we have a little bit of an example. So some things might absorb the ultrasound waves. Some materials inside the body might reflect them back, and it's detecting these things. Also, some things could scatter the wave out so it doesn't come back cleanly. Or we have that refraction where there's some material where the wave is still traveling through it, but the speed is different between those two things. So you send the waves into the body and then detect the signal that is sent back after it's reflected or refracted or absorbed, which then you wouldn't actually get a wave back in that case. And it just shows you different materials inside the body. So if you're trying to get a look at some organ, the outside of the organ will reflect stronger than the inside, giving you a clear image of that. And then finally, ultrasonic waves. Animals use ultrasonic waves to get a layout of their surroundings. Bats and dolphins do this, for example. People can also learn to do this. You have to adapt to it, but your brain can be trained to hear the sound reflecting off different surfaces and generate a layout of your surroundings. I actually remember hearing about a guy who was blind who would do intense hikes and climb huge trees, and he could do all of that because he used sound to get the layout of his surroundings instead of sight. So anyway, that's just like a cool aside. So that's all I have for you today. Have a great day.